Hi class, we are now on our last section of chapter 11. This is 11:10, gases and chemical reactions. So when we, in reactions involving gaseous reactants or products, the amount of gas is often specified in terms of its volume at a given temperature and pressure. So this is where the ideal gas law comes in to convert pressure, volume, and temperature to moles. We use stoichiometric coefficients to convert to other quantities in the reaction. So this may not make sense, but basically what it's saying is that we are given a specific amount of variables, and if it's not moles, then depending on what type of reaction is, we can determine the moles, and then from there we can look at a reaction, a balanced equation, the coefficients, to determine what another product or reactant is in that equation, in that balanced equation. So let's take a look at a problem. How many moles of ammonia are formed by the complete reaction of 2.5 liters of hydrogen at 381 Kelvin and 1.32 atm? Assume that there is more than enough nitrogen. So what we're given is, first of all, it wants to know how many moles of ammonia, but we're given no information on ammonia. We're given information on hydrogen. So we're going to have to use the information on hydrogen first, then we can go and, based on the balanced equation, get the information on ammonia. So we're given the volume, we're given the temperature, and we're given the pressure. With these three variables and the gas constant, we can solve for the moles of hydrogen. So in this case, we set everything up, isolate N, and it gives us our value for the moles of hydrogen. The next step is to now use the balanced equation with the coefficients to determine the amount of moles of ammonia. So in this case, we have 3 moles of hydrogen for every 2 moles of ammonia. We set that up here, and this produces 0.070 moles of ammonia. So now we're going to take a look at standard temperature and pressure. I briefly discussed this or said something about it in a prior section, but we are now at that section. So this is standard temperature and pressure. What this is the volume of gases can be compared as standard temperature and pressure when they have the same temperature and pressure. So we can compare gases if we match them, we make sure that they have the same temperature and the same pressure. We can then see what the behavior will be. So we kind of, in a sense, force these gases into force these gases into these certain conditions, and those conditions being 0 degrees Celsius or 273 Kelvin and 1 atm or 760 millimeter mercury, or anything equal to 1 atm. So in this case, now we've covered temperature and pressure, but we didn't discuss volume. Volume is on this page, and we discuss this, and we call it molar volume at STP. So the volume for a gas, and all gases at STP, is 22.4 liters. Doesn't matter what the gas is. If it's at STP, then it is, right here you can see 1 mole is equal to 22.4 liters at STP, the molar volume. Or if the word molar volume is used, this is what they mean. 1 mole is equal to 22.4 liters. So we covered what the standard temperature and pressure would be, and the molar volume is 22.4. This can also be used as a conversion factor, which we will use in a problem coming up. So just to make sure you understand, here's 1 mole of helium, 1 mole of oxygen, 1 mole of nitrogen. They all have different molar masses, but they are at STP, which is a temperature of 273 Kelvin and a pressure of 1 atm, which means they are all equal to 22.4 liters. Doesn't matter what the gas is. If it's 1 mole, the volume is 22.4 liters. And this just says the same thing. It's just comparing it. Okay, so at standard temperature and pressure, if we want to use the molar volume, you would use it as an equation. You can use it as a conversion like this. This is simply, as long as you're very comfortable understanding 22.4 liters equals 1 mole of gas, you can set it up for a conversion factor. And you have to make sure you understand what STP conditions are. Now here's the thing. Problems don't always tell you what the conditions are or remind you what they are. They'll just tell you it's at STP conditions, and this is one of those things that you're just supposed to understand, that is what the conditions are. 273 Kelvin, 0 degrees Celsius, 1 atm. So let's do a problem. What is the volume occupied by 2.75 moles of nitrogen gas at STP? This is a perfect example. It doesn't tell you what the STP conditions are because you're supposed to know them, but it does mention STP. So first things we do, pull all the information we have. We have 2.75 moles at STP, key being STP, and we need to know the volume of a gas at STP. Now this is, we have a certain amount of moles, so we know what the conversion is for this, but you can't completely say right off the bat that this is 22.4 moles. For 1 mole, it equals 22.4 moles. However, we are starting out with more than 1 mole, so we're going to have to use that as a conversion. So we're going to go from moles of nitrogen using the molar volume to get the volume of nitrogen. So next thing is we set up our conversion factors so we know which way to use them. And in step 4, we just plug the problem in. So 2.7 moles. We use a conversion factor of 1 mole of nitrogen on the bottom, 22.4 liters on top, and that produces 61.6 liters of nitrogen. Let's do another problem. What is the volume at STP of 4 grams of methane? So this is asking for methane, and it's asking for the volume of 4 grams of it. But the thing is, it's at STP conditions. So we pull all the information out that we know, but we also need the volume of it. So here is the stepping stones for this. We have the mass of methane, which does not work for us. We're going to have to convert that to moles by using the molar mass. Then when we get the moles of molar mass, this will be very similar to the previous problem. We can do the molar volume, and then we can get the volume of methane. So we have our conversion factors here, and we simply set it up. So this can be done in one complete calculation. We have our 4 grams. We have our molar mass of methane. We use our conversion of molar volume, which is 1 mole of methane is equal to 22.4 liters, and the volume of methane is 5.58 liters. How many grams of helium are present in 8 liters of gas at STP? So again, here's STP. So pull out the information, understand what it's asking for. And in this case, it's asking for grams of helium. We have a volume of 8 liters, and this is at STP. So we're going to go from volume of helium to molar volume to moles of helium, molar mass to mass. And if this doesn't make sense, hopefully it does when I show the problem. So the first things you need is you need to know that 1 mole of helium equals 4 grams of helium. We have 22.4 liters, which is the molar volume of 1 mole of helium. And then we have our other conversion factors that we can use. So we set this up with 8 liters. We do 1 mole on top, 22.4 liters on the bottom. That gets us to 1 mole of helium, which is 4 grams of helium. And that will give us, because this is the molar mass right here of helium. And this produces 1.43 grams of helium. And I think this is our last problem. Calculate the number of liters of gas that forms at STP when 0.879 moles of calcium carbonate undergoes this reaction. So we have calcium carbonate as a solid, and it decomposes to calcium oxide and calcium carbon dioxide. So what is this asking for? This is asking for volume again. So in this case, we're going to set up with the 0.879 moles of calcium carbonate. We're going to look at the reaction. We have 1 mole of calcium carbonate, 1 mole of CO2, and then we take the 1 mole of CO2, but this is at STP, so we know what the molar volume would be, and that's 22.4 liters equals 19.7 liters of calcium dioxide.